This is 30 minutes of AP exam for Physics 1 review, and I'm going to go over work and energy multiple choice questions in this video. So let's look at one of the first questions. In this question, they say that an amusement park ride has two identical carriages that revolve around a center of the radius axle. As shown in the figure, both carts travel at the constant tangential speed at all points along the circular path. At what position is the total mechanical energy of the those two carts, Earth system at its maximum value? So if they said Earth system, they would mean just one cart. But here they say cart, Earth system, so they mean two carts. So you can have, I'm going to draw a few cases right here. So here is the first case. So let's say I have the cart on the top and on the top. So if I say this is potential energy 0, then potential energy here is mg. Instead of h, I'm going to write 2r. Because if this is the radius of the ride, of the circular ride, then the height at which it goes from the bottom to the top is 2r. And they both have kinetic energy, so the kinetic energy here is 1/2 mv squared. And let's say the velocity is in this direction, and the velocity is in this direction, tangential velocity, and it's constant. And the kinetic energy right here is the same, 1/2 mv squared. So the difference between point 1 and point 2 is just the potential energy. So that's if you had the cart on the top and on the bottom. What if you have the cart at different positions? So if I have the cart over here and over here. So if this is some position x, and this is some position x, away from the bottom and away from the top, then the potential energy right here is equal to mg, and I have 2r minus that position x, and the potential energy right here is equal to mg times x. And then still you have the kinetic energy of both, which is 1/2 mv squared, and kinetic energy right here is equal to 1/2 mv squared. So if we add kinetic energy above and kinetic energy at the bottom, this total energy added together is equal to the total energy that you had in the two-cart system before. So this total energy right here between these two and total energy at the bottom is the same. So it doesn't matter where these two carts are going to be. The total energy of the system is always going to stay constant. In this question, they say a simple pendulum consisting of a sphere tied to the end of the string of negligible mass. The sphere is pulled back until the string is horizontal and then released from rest. Assume the gravitational potential energy is 0 when the sphere is at the lowest point. At what angle is the string made with the horizontal when the kinetic energy and the potential energy of the sphere Earth system is equal? So the potential energy right here is equal to mg, and r is the height, and the potential energy right here is equal to 0. So no matter where we look in the system, it should be equal to, together in the system, mgr. So when you have the sphere in this position, I'm going to say this angle is 30 degrees. Or maybe in this position when you have 45 degrees. Or in this position when you have 60 degrees. The tricky part right here, even I made a mistake when I made it first time to solve this question. I look at the angle with the vertical because we used to that this is 0, this is 30, this is 45, and this is 90. but they're looking from the horizontal, so you have to read the question very carefully. So if I look at this one, the first one, where I have 30 degrees, then I'm going to look at this triangle right here. So I have right here this triangle, and this is the right angle. Then this is L, or R, let's keep it R. So this is R sine theta. And at this point, your potential energy is equal to mg, and the height above the ground, or above the point where we say potential energy is 0, is r minus r sine theta. Then how much kinetic energy do you have at this point? Kinetic energy right here is 1/2 mv squared. But that is how much energy is lost from the top point to this point. So from all the way at the top to this point, and potential energy lost is equal to, maybe I'm going to rewrite my potential energy so it's easier to see, to compare them. So it's equal to mg. If I take r out, I have 1 minus sine theta, or in other words, I have mg r minus mg r sine theta. So you see, this is how much potential energy is lost compared to what we used to have. Then that is how much energy I have now in the kinetic energy. So the kinetic energy at that point, at 30 degrees, is equal to mg r sine theta. And in this case, we chose theta to be 30 degrees. So the potential energy at that point is equal to mg. And then I have, right at this point, right? So I have r. And then I have 1 minus sine of 30, which is 1/2. And the kinetic energy is equal to mg r. And then I have sine of 30, which is 1/2. So potential energy at that point is equal to mg r times 1/2, and equals to the kinetic energy at that point, mg r times 1/2. And the question is asking you, will the angle with the horizontal, you have to be very careful right here, will the angle with the horizontal be greater than 45, equal to 45, or less than 45? And we can see that it is less than 45. I could also check this for 45 degrees and 60 degrees from the horizontal, but I see the first angle that I checked has worked out. So my kinetic and potential energy equal to each other when I have 30 degrees with the horizontal. And again, I made a mistake first time when I was solving this question because I did not read carefully the problem. So every time you have multiple choice questions on AP exam, read it a few times and pay details to the point, like the angle with the horizontal. In this question, they say a ball is tossed straight up and later returned to the point from which it was launched. If the ball is subject to air resistance as well as gravity, which of the following statements is correct? So the air resistance is not negligible in this question. So if there was no air resistance and I tossed the ball with some initial velocity, I'm just going to choose some velocity. So I'm going to say 40 meters per second. Then the time it would take to get the ball to the top is change of its velocity over the acceleration. So the final velocity all the way at the top would be 0, the initial velocity 40, and it's a deceleration of 10. So it would take 4 seconds for the ball to get to the top. And it would take 4 seconds for the ball to fall down. And the ball would have exactly the same velocity, 40, when it reaches the ground. But there is air resistance. So because there is air resistance, I'm going to throw the ball up at 40 meters per second. but because of the air resistance, maybe it will reach the top in 3 seconds, not 4 seconds. Now, if there was no air resistance, it would fall down in 3 seconds and would have 30 meters per second. But because there is air resistance, then it will not fall down with 30 meters per second. It will fall down even in with the less velocity because of the air resistance. Even if it takes longer time, it may not reach the 40 meter per second velocity because it never got to the same height. So it never had the same potential energy to reach that potential energy, kinetic energy, to convert that potential energy to the kinetic energy. So the answer for this question would be the speed at which the ball returns to the point of launch is less than the speed when it is initially launched. In this question, they say a block of mass m is released from rest at the point 1, as shown in the figure. The block slides without frictional force along the circular path or arc, but encounters frictional force as soon as it reaches the horizontal portion of the track at point 2. The block travels the distance d and then stops at point 3. Consider the block Earth system. In terms of the mechanical energy, the system which of the following claims is correct and why? So the closed system is referred as to system in which there is no loss of mass, energy, change, and also in a closed system the temperature or volume or pressure are kept constant and are not affected by external forces from outside of the system. In an open system, these values can change and probably do not remain constant for long. So if the system is isolated or closed system, then the total momentum before a collision or explosion equals to the total momentum of after the collision or explosion. And on the other hand, the conservation of energy also only applies to a closed system, meaning that the system that can exchange energy with the environment. So if we look at the universe, for example, then universe would be a closed system, while a coffee cup slowly cooling down on the countertop is not a closed system. So if the system can exchange energy with the surrounding, it is not closed system, and conservation of energy does not apply. So in an open system, the mechanical energy will lose or gain some of it, mechanical energy, depending upon the outside forces. So good examples of a closed system would be, like, let's say, two cars that are colliding on a track elastically, or two air cars that are colliding on a track and sticking together, or a bullet being fired into a hanging wooden block and becoming embedded in the block, with the system then acting as a ballistic pendulum. But an example of the open system would be a bullet being fired into hillside and becoming buried in the earth, because after all that energy is going to be transferred into, we don't see any energy after the collision, so the energy was not transferred into another type of an energy that we can see. So in this question, when they ask you, will the mechanical energy of the earth block system change or stay the same? Because when the block is sliding from point 1 to point 2, there is no friction acting, and between 1 and 2, the system is closed, because the only force that is acting on the block is the acceleration due to gravity. But then between 2 and 3, the block starts to slow down because of the friction. So if we talk about earth and block system between 2 and 3, then it is not conserved. The energy would not be conserved, because the energy is being transferred to the friction force or the other external forces acting between block and earth, and that would be the friction force. So in this case, the system is open, and the mechanical energy is not going to be conserved. The mechanical block earth energy is not going to be conserved because there is a net force exerted on the block that slows down its mass. In this problem, they say an inclined track is secured to the table. The height of the highest point of the track above the table is h1. The height from the table from the ground is h2. A block of mass m is released from the rest and slides down the track such that the frictional force are considered to be negligible. The block leaves the track horizontally and strikes the ground point at the point distance d from the edge of the table. And then, which of the following statement is correct about this scenario? And they're given two answers for this problem. So the answers they give you here, and you have to be very careful with the wording. If the block is released from a height 2h1, the block will land at a distance of 2d away from the end of the track. And let's look at some solutions for this problem and see if that is true for this multiple choice question. If h nu1 with a dash 1 is twice the original h1, then the velocity right here at the end without the friction, all the potential energy would turn into the kinetic energy. So your potential energy nu would be equal to mg and twice h1, and would turn into the kinetic energy also nu, not the same as previous one, 1/2 m v squared, and that would be this velocity. And that velocity would be equal to, so I can cancel m from both sides, and it will be equal to the square root of 4gh1, which is equal to 2gh1. But originally, it wasn't twice h1. So if originally h1 was just h1, then your final velocity would be equal to the square root of 2gh1. So if you compare this with this, you see that, and the time is the same for both of them to land. So the time before you increase h1 and after you increase h1, the time from the moment it leaves the table to the moment it falls on the ground is the same because h2 did not change. So the time is the same, but the velocity is larger for the one that is increased the height. So that means it will land farther away, but not twice as much, because the difference between this velocity and this velocity is the square root of 2. So the distance would be, the new distance would be the square root of 2, the old distance. So it wouldn't be the same twice distance or the same distance, and it wouldn't be twice as long if you increase h1 by 2. For the second one, they say if the block's mass is increased by 2m, will the block land 2 times the distance? And we saw that the potential energy, when it is equal to the kinetic energy, I have mg and h1 is equal to 1/2 mg and 1/2 mv squared. So this is 1/2 mv squared. You see that the masses cancel and the velocity does not depend on the mass. So it doesn't matter what you do to the mass, the velocity is still going to stay the same because it depends on the height h1. The next choice they give is the total mechanical energy of the system consisting only the block. Here is another tricky part. The energy consisting only the block increases from the moment of release to the moment it strikes the ground. So if I consider the energy of the block Earth system, then the energy, mechanical energy, would stay the same because you have potential energy right here that would be transferred to the kinetic energy over here, and then to bigger kinetic energy over here because you added more potential energy with H2. So the block Earth system would stay the same because there's no friction and the energy just transfers from one to another. But they don't say it is the block Earth system. They say the total mechanical energy of the system containing only the block. And if we're talking about the block alone has no clue where it is located. It has no clue any relationship to the Earth. All it has is zero energy of any type of energy when it is on the top of the incline, because we consider the energy of the block is zero where it is located and it's not moving with any velocity. And by the time the block is striking the ground, it has some kinetic energy. So the mechanical energy of the block is going to increase by the time it hits the ground. So the total mechanical energy of the system containing the block alone will increase as it moves from the top to the bottom until it hits the ground. And another choice in this multiple choice problem is that the total mechanical energy of the block Earth system remains constant. And yes, the total mechanical energy of the block Earth system is constant. So there's two answers. One is the total mechanical energy of the system containing only the block is increasing, and the total mechanical energy of the block Earth system remains the same. This is how tricky some of the multiple choice questions are on AP exam. Here I'm going to look at two blocks, and in one of them the person is holding the block at rest a few feet above the table, and the person then lowers down the block and slows it down to the constant speed as it places the block on the table. Which of the following accurately describes the change of the total mechanical energy of the Earth block system? So on the right I have this block 2. So this block 2 has potential energy, which is mgh, and then it will turn into the kinetic energy. So all that energy is going to be equal to also mgh, or 1/2 mv squared. So here block Earth system is conserved because the Earth is acting on the block and accelerates it. It loses potential energy, but it turns into kinetic energy, same amount of kinetic energy. In the second problem, it moves with a constant velocity. So this final velocity is going to be much larger than the one that when the person placed the block on the table. So because the energy of the block does not increase because of Earth, because the hand is doing some work on the block, and the block does not have as much kinetic energy. It has some kinetic energy, but not all of it that it would have if the block was falling down. So the block has the total mechanical energy decreasing because the person does negative work, takes away some of the energy from the block and forces the block to move at the constant velocity, not to accelerate. In this question, they say that a potato falling vertically downward is struck by a dart that is traveling vertically upward, as shown in the picture. The dart and potato then collide, stick together, and continue moving after the collision. So the weight of the dart is given W, and which of the following claims best describes the magnitude of the net force on the dart immediately before, during, and immediately after the collision of the potato? And the answers that they gave you that, so let's actually make numbers and see how that will work. So before the collision, the weight of the dart is the only force of gravity that is acting on the dart, which is 2 newtons. And during the collision and right after the collision, because they stick together, the weight exerted on the dart is greater because the potato, which is 10 newtons, and the dart, which is 2 newtons, together will make the weight that is acting on the dart. So the weight of both of them during the collision and after the collision will be greater than the weight of that the dart is experiencing right before the collision. Let's look at this problem. So I'm going to draw the forces that are acting on my masses. So it's the tension and force of gravity. So I have tension M1G, tension M2G, and acceleration in this case is going to be down, and acceleration in this case is going to be up. If I write the equations for my system, I will have, and if I solve for acceleration, then acceleration is going to be G, and then I'll have M1 minus M2 divided by the sum of both of them, M1 plus M2. And in this case, the acceleration is going to be equal to 1.43 meters per second squared. So that is meters per second squared. So let's say that would be ideal, and but they actually measured the velocity of the blocks or to measure the acceleration eventually. So they measured the distance, maybe the velocities, and figure out that acceleration of the blocks wasn't 143. Let's say the acceleration that they measured, so it's the measured acceleration, is actually 1 meter per second squared. So the calculations that should be did not match that what actually was. So because they don't match, you know that there is the difference of the acceleration, and that is equal to 0.43 meters per second squared. Then the question is here, what is causing this acceleration? And the acceleration change is caused by the friction. So how much is the force of friction? So if I want to calculate the force of friction, or sometimes I don't write this way, sometimes I write the friction force like this, is equal to the total mass, which is 4 plus 3 kilogram, times the change of the acceleration, and that will give me the force of friction in this case is equal to almost 3 newtons. And it could be force of friction, air resistance, all of the forces that slow down these masses and don't allow the masses to reach the acceleration of 1 meter per second squared. So I went away a little bit from the work and energy and solved two questions, one related to momentum and one is to forces, or force of friction dynamics. But I'm back to energy, so I'm going to show you this graph to explain what else you can see on AP exam that you should be ready for. So let's say I have this problem and the car is moving on a level track in the positive direction X, the force is acting in parallel axis X, and the graph shows the net force exerted on the cart as the function of the displacement as the cart travels from x equals to 0 to x equals to, we have 7 meters. What is the net change of the kinetic energy of the cart? So at first I'm going to see what this graph represents. So the area underneath the graph is force times the distance, and force times the distance is equal to the work done on the cart, and that work is actually the change of the kinetic energy of the cart, and equals to, so the force is 10 and the distance is 3 meters, so that gives me 30 joules. And then for the second part right here, the negative force is exerted on the cart, so there's still force times the distance and equals to change of the kinetic energy, and that is equal to negative 5 times 4, and that gives me negative 20 joules of energy. So at first the cart gains 30 joules of energy, and then it loses 20 joules of energy. So the kinetic energy that was gained by the cart is 10 joules. And it's depending what kind of graph you're given. In this problem, it is 10 joules. For different numbers, you would get maybe negative energy, so the cart lost 10 joules of energy. But in this case, we see that the cart gained 10 joules of energy. And I'll stop here. This was our review for the AP exam questions, AP Physics 1. And thank you for watching, and I'll see you in the next video.